we are discussing optimization, that is finding the maxima, minima of a function fxy, okay, with respect to a constraint gxy equals to c. Okay, so we already know the necessary condition for the optimum value to occur. The necessary condition was the partial derivative of fx divided by the partial derivative of fy is equal to the partial derivative of g with respect to x divided by the partial derivative of g with respect to y. This was the necessary condition. We can equivalently write this as fx upon gx equals to fy upon gy. That means these two ratios should be equal. Now, we introduce a method known as Lagrange multiplier method. Now, what is this? Assume that this ratio fx divided by gx equals to fy divided by gy equals to lambda. Okay, because these two are equal, so we can assume that they are equal to some constant lambda. So that means f of x is equal to lambda times gx and f of y is equal to lambda times gy. Okay, or equivalently, this means that fx minus lambda times gx equals to 0 and fy minus lambda times gy equals to 0. Okay, so now we are going to develop a method. So let us define a function, a Lagrange function x of x, y, and lambda, okay, which is defined as f of xy minus lambda times g of xy minus c. We have this thing, okay? Now, we can see that when we partially differentiate L with respect to x, we will have f of x minus lambda times g of x. Because c is a constant, so its derivative is going to be 0. Similarly, when we will have L of y, we will have f of y minus lambda times g of y. Okay, and we will have L of lambda. So that is, now we are differentiating f with respect to lambda. F is only dependent on x and y. So this is going to be 0 minus the derivative of lambda is 1, gxy minus c. So we already know that. Now what is happening, that we know that 1, 2, and 3 are holding. So we know that 1, 2, and 3 are true. So it would mean that L of x is equal to 0, L of y equals to 0, and L of lambda is equal to 0. Okay. So these are equivalent conditions. Now, therefore, we will be solving these two equations along with this equation to find the point of optimizations or maxima or minima. L of lambda equals to 0 is equivalent to g of xy equals to c. So we can say that solve Lx equals to 0, Ly equals to 0, and g of xy equals to c to find the point of maxima and minima, or maxima or minima. Okay. Now, for example, we have this question. Maximize f of xy equals to xy subject to 2x plus y equals to m. Okay. Now this problem is framed like this. We have to find the maximization. So it is given in the problem that we have to find the maxima only. The optimum value will come out to be maximum. Okay. So Basically, here your fxy is given to us. Here, this is your g of xy equals to 2x plus y. So actually gxy, minus m, you have to consider this particular thing. Okay, so we will be defining L of xy equals to f of xy minus lambda times g of x comma y minus m. So that means L of xy would be xy minus lambda 2x plus y minus m. Okay. So L of x equals to 0 is equivalent to saying that y minus lambda 0, 2 plus 0 minus 0, okay, equals to 0. So this implies that y equals to 2 lambda. L of y equals to 0 is equivalent to saying, see, we are calculating the partial derivative of L with respect to y now. So the partial derivative with respect to y of xy will be x minus lambda. And now this is 2x, partial derivative with respect to y will be 0. For y, it is going to be 1. So this would imply that x is equal to lambda. Okay. So we have y equals to 2 lambda, x equals to lambda. So these two equations, now what we have to see? This. So 2x plus y equals to m. So that means 2 lambda plus 2 lambda equals to m. So 4 lambda equals to m. This would imply m equals to or lambda equals to m by 4. So from here, we are going to get x equals to m by 4 and y equals to 2m by 4, which is going to be m by 2. So the optimum value occurs at m by 4, comma, m by 2. So this is how we apply the method of Lagrange multiplier to calculate maxima or minima of a function of two variables with respect to an equality constraint.